Good morning, everyone. I want to welcome you to another multivariate statistics class. Before I get started today, I'm actually going to make a series of announcements. I'm going to say I've graded problem one and problem two of the midterm one for all students. And of course, I'm going to start grading problem three today. So, like I said, before the end of the week, you're actually going to receive your results, for midterm one. Even though I know that we are currently experiencing, extreme weather, I will advise that students should come regularly to class, because getting A in a course, okay, requires a lot of commitment from students. So the number that I saw during the midterm, okay, is significantly higher than the number that have been attending lectures. So uh, I record my lectures. My lectures are posted on YouTube for, you know, I actually do that for give student another opportunity. So it's either when you attend my class, you can also watch my videos, and if you need clarification, of course, office hour is there for you to, make use of the opportunity of the office hour. So the office hours are conducted on Zoom. You can be anywhere in the world, to attend my office hour. And let me say this, things are going to become more complicated because we are now in advanced stage of this course. And that is why I need you to pay more attention to what we're going to be doing. Okay, so we're still on the same material. We're going to use this same material today and Friday. And of course, the focus today will be on inferences about multiple mean vectors. Before now, I walk you through inferences about a single mean vector. A single mean vector actually implies that we are referring to a single setting. Okay, single setting with multiple variables involved. And of course, I walk you through how to conduct statistical inference on a single vector. On that, where you learn how to construct confidence interval. Remember, I walk you through different kinds of simultaneous confidence interval. Okay, I walk you through the classical T confidence interval. I walk you through the Ottolini squared confidence interval. I remember Bonferroni and also the last sample confidence interval. And of course, I remember I also walk you through how to test hypothesis when the single vector is hypothesized to have some values. Today, away from a single vector, we actually want to move into situations where we are no longer having a single group, but two groups. So the focus today will be on two groups, while the focus on Friday will be on more than two groups. Okay, you can see the way it is structured. Now, in the outline for the multiple mean vector, of course, I'm going to have an introduction. I'm going to talk about a paired comparisons. I'm going to talk about repeated measures. I'm going to talk about two populations. Okay, so that is where we're going to stop today. Of course, Friday, we're going to continue, from one way multivariate analysis of variance. Now, for you to be able to understand, okay, the two groups that we want to talk about today, I first want to have a kind of a recap on univariate, two groups with univariate, because for you to be able to understand two groups with multivariate, you need to first have a recap, or on two groups involving univariate. Univariate means only focusing on one variable. Okay, now I want to remind you that we have when we got two groups. Okay, at times we may be working with dependent samples, and we may also be working with independent samples. When you are working with dependent samples, of course, we normally talk about a paired t-test, situation where subject was visited in more than one occasion, specifically in two occasions. And of course, the independent samples, I got two different, groups, okay? And of course, I'm comparing. Now, I just wanted to see for univariate, reminder that, when we're focusing on two sample t-tests, we could focus on dependent samples, we could focus on independent samples, because this idea is also going to be extended to multivariate setting. So which means in the multivariate setting, we're also going to have dependent samples, or we're also going to have independent samples. Okay, so if you take a look at as a reminder, for the dependent sample, of course, we normally test these two hypotheses. Um, well, the mean of the difference is hypothesized to be a mu naught, and the mu of the difference not equal to mu naught. Of course, we test this hypothesis that we're testing here. If it's for dependent samples, what we mean by dependent samples, so it's like we're taking observations, we are visiting subjects in more than one occasion. We're using the same subject, okay? We get readings for before, reading based on one variable before, then we get reading based on the same variable after. Okay, so the fact that we're focusing on the same individuals, except that they are being visited in two occasions, okay, make dependent sample t-test to be appropriate. And of course, when we have independence, on the other hand, independent on the other hand means I'm not using the same subject. The subject I'm using in this group is different from the subject that I'm using in another group. So therefore, they are assumed to be independent. So, and what we want to do is to test equality of means. Okay, we want to test equality, of means. So testing the equality of means, okay, we're actually going to use sample t-test for independent samples. Okay, now that you understand the univariate, okay, conducting sample t-test in the univariate, of course, whether to use a peer t-test or to use two sample t-test depends on whether you're working with dependent samples or independent samples. Now, what we want to investigate now, okay, we actually want to go beyond univariate. We have more than one variable at a time, even though we want to compare two groups. We want to compare two groups, but we have more than one variable, okay, at a time. It could be two variables, it could be more than two variables. Now, we want to have a way to extend okay, or the two sample t-test in a multivariate way, okay, and that is exactly what we're trying to do here, okay. So, in doing that, if we first want to start with dependent samples, of course, with dependent samples, when we're only focusing on one variable, is the appropriate t-test is going to be called a paired t-test. But right now, we have more than one variable involved. Okay, can we have a way to derive the um the multivariate version of the paired t-test from the univariate angle? And that's exactly what we want to do. Like I said, where we are now, we are in a critical advanced stage of this work, of this course. And the moment you don't understand, please ask question. Another exam is around the corner. Okay? Another exam is knocking at the door. So if I were you, okay, you don't understand anything, let me know. Ask question. Now, what do we want to do here? If I want to conduct a PRT test where I'm focusing on just one variable, like I said, this is going to be the specification of hypothesis. This is going to be the test statistic that I'm going to use. And of course, the D bar is just the mean of the difference. How do I get a difference? The difference is just going to be the difference in the variable measure, okay? Before and after. We're measuring that before and after on the same subject. Imagine you're trying to investigate the effectiveness of maybe a physical therapy program, okay, on the performance of an athlete, okay, and you actually um, want to consider before and after the therapy. What do you want to measure? Maybe probably you want to compare agility. Okay, maybe you want to compare agility or reaction time, okay, of this particular patient, or you want to compare endurance, okay, endurance. Okay, so you may want to compare, okay, like I said, you want to measure the effect of a new physical therapy, okay? You want to investigate the effect of a new physical therapy, okay, on maybe athletes on athletes performance, okay, on athlete performance in relation, maybe on in relation to physical test. So the physical test, maybe that you're talking about, you want to put into consideration, maybe the variable that you're considering is endurance. Okay, endurance of the athlete, endurance in minutes. Okay, now if you want to do that, okay, you're actually going to use the same set of athletes. Okay, what was the endurance before applying the physical therapy? And what was the endurance after applying that? And that is, you're actually going to need a difference between them. Okay, the difference between the endurance before and after application of the physical therapy. Okay, and of course, you for each subject you find the average. The average is the D bar. Okay, and you find the standard deviation of the difference. Okay, that's what you see here. This is what univariate case appeared, t-test for univariate case. And at the end of the day, you're going to take a decision on how effective is the physical therapy program. But you know what I'm going to do right now? And so if that is the test, we also have a confidence interval. What you see here is a confidence interval. I'm still focusing on the univariate case. Don't forget, statistical inference actually come in two ways. It comes in terms of hypothesis testing and also come in terms of confidence interval. Now, all what I'm trying to show you now is for univariate case. But how do we derive the multivariate version? Maybe, and I want to change. I'm not only interested in endurance, okay? I'm also interested in agility. I'm also interested, um, you know, in reaction time. Reaction time, okay? I'm interested in agility. I'm interested in, reaction time. Now, I got X1, X2, and X3, okay? And of course, I will be able to have opportunity to see whether there's a difference in the mean or between the I will be able to measure the effect of the new physical therapy on the athlete based on not only a single physical test, but this time around multiple tests. Going to have a test on endurance. This is in minutes. This one is seconds. Okay, agility in seconds, and this is in milliseconds. Okay, milliseconds reaction time. Okay, now if I actually want to do that, okay, we need a multivariate approach, which is what I'm trying to set up here. We have a DI, go to the difference, and that's we're actually going to assume that the DI follow a multivariate normal distribution without and assuming the subjects are independent to start with. Then from there, I'm actually going to apply Ottolini squared for different score vector. The score now is going to be vector. And if you take a look at what I have here, okay, so what I'm trying to say, if I want to take a decision, okay, regarding that, I need to compute the Ottolini squared. The Ottolini squared here is based on difference, okay? The D bar, it's not just going to be a single mean, but the D bar is going to be a sample mean vector. That D bar is going to be a sample mean vector. Why do you have sample mean vector? Okay, the first mean in the vector is going to be the difference between using the new physical therapy and without the physical therapy on endurance. What is the mean of the difference across subjects? The mean of the difference across subjects before therapy and after therapy for endurance. So we're going to have a D bar 1. Then for agility, D bar 2. For that, D bar 3. Okay, so that's why the D bar is going to be a sample vector. Okay, it's going to be a miss. Then, of course, we're also going to have the inverse of a sample covariance for that. And for us to be able to take a decision, we're actually going to compare the T squared with that guy. We're comparing the T squared with that guy. Okay, comparing the T squared with that guy. Okay, now if you take a look at what I have, okay, reject H naught. Now, when you take a look at the H naught here, the H naught here is actually the population mean of the difference. Population mean of the difference, that mu D is a vector. Okay, it's a vector, population mean of the difference. And of course, the only conditional that we wish to reject is when the T square is greater than that. Okay. Now, here you are actually testing hypothesis. Now, what I'm trying to tell you now, this is a multivariate version of a PRT test. Multivariate version of a PRT test. Now, uh, this is happening, for two occasions. I'm actually visiting subject in just two occasions, the same subject in two occasions, but what was measured is more than one variable. What was measured was endurance, agility, and reaction time, which make it multivariate. Does that make sense? Okay, but what if in a situation whereby we visit the a more than two occasions instead of two occasions? You know, the example that I use here is new physical therapy against the conventional therapy they've been using. Okay, so which means the same subject will be given the conventional therapy. The same subject will also receive the new therapy, and three variables, more than one variable will be measured. The first variable, like I said, is endurance. Okay, the second one is agility, and the third one is reaction time. Okay, I wanted to take note of that. But what if in a situation whereby we want to consider more than two, more than two visits? We're visiting the same subject more than two times, and that will lead us to repeated measurements. Repeated measurement. I said in a repeated measure design, the unit participates in Q greater than 2. Q greater than 2 means more than two times. The subject will be visited in more than two times. How do we, derive, the multivariate version of the repeated measure? Of course, in statistics, we have a repeated measure ANOVA. Okay, a repeated measure ANOVA that we have is based on just one variable, univariate. But right now, we want to extend that to multiple variables. Okay, and I'm going to give an example. I'm going to give another example. Now, if a researcher is trying to investigate effect, okay, a researcher is investigating, okay, effect of hydration level. Hydration level. When I say hydration level lower, medium, and low, medium, and high. Okay. Now, if we want to measure the effect of hydration level, okay, on the performance, maybe in order to improve, the performance, in order to improve performance of athletes. Okay, in order to improve performance of athletes on multiple multiple physical tests. Okay, let me give the example of the physical test. Okay, so this time around, probably I still want to use the same example that I used the other time. Okay, the physical test, maybe I'll talk about endurance, I talk about agility, and I talk about reaction time. So maybe this researcher is actually a sports scientist, okay? A sports scientist is actually investigating that, okay? How that affect different hydration level, affects, the performance across multiple physical tests. And that's you know, uh, multiple physical tests. I think I'm going to put it this way so that you understand. You say the repeated measure. Uh, okay. So, effect of on multiple physical tests over time. Okay. Now that's going to be a repeated measure. Now, what happened here is that the same participant is actually going to be observed across this and under uh, different hydration condition, under different hydration condition. Okay, so if you take a look at what I have right now, okay, the idea of a multiple test. Okay, so what is the difference between this and the one we did the other time? Because here, how many groups? It's more than two groups. Okay, one, two, three. Okay, that's really make it a repeated measure. Okay, if I only have two, of course, I'm still going to be talking about, two groups. Okay. The level of categorical factor determine the numbers of groups that we have. Okay. Now, if I want to do that, okay, then I need a contrast matrices, developing that. I need you to pay attention. We are in a very critical stage. Okay. Now the contrast matrices, here, mu1 minus mu2. Okay. Now the mu1, what is the coefficient of for the mu1? 1, right? What is the coefficient of the mu2? -1. Now, because I'm only considering difference between mu1 and mu2, every other thing is going to stay 0. That's what we mean by contrast. Now here, mu1 minus mu3. Mu1, what is the coefficient of mu1? 1. What is the coefficient of mu3? -1. Every other one stays 0. The one I'm considering, okay, the one I'm considering will be 1 and -1. The one I'm not considering is going to be 0. That's what that means. And that's why I have this matrix. And I have a mu1, mu2, and that. And that is, we can refer to that as C1 mu. Okay. Now, because the moment you understand your C matrix, okay, the test statistic is going to be easy. Now, I wanted to pay attention now. Okay. Now, I'm going to show you what is the t-square in this regard. The t-square in this regard is actually this guy. You're going to see that that's a combination of a C that I talk about, the contrast that I talk about the other time. You can see N, CX bar. Okay, you can see everything is in terms of C and X, sample covariance. Take a look at that, and the sample mean vector. So the moment, and where is my C coming from? Okay, please pay attention. If you don't understand, ask me a question. Where's my C coming from? You see where my C is coming from? You see that? You see where my C is coming from? The C is a contrast. Contrast. Okay? Now, we use contrast in comparison, like in difference of the linear combination of the means. Okay? Now, under the hypothesis, look at what we're testing. We're testing that that is that versus that is not that. Okay, now if you don't understand what is the mean, the sample mean vector, this is how to get each of the mean, the formula, then you can see this one, the sample covariance remain the same. We've already done all of that in this class. Okay, now we can also have a simultaneous, like I said here, this is when you how to conduct the test, what the test statistic is, and how to take your decision. Look at that. T squared, the moment you get your T squared, you compare all of that with n minus 1, q minus 1, divided by n minus q plus 1 and f that you check under a particular significance level. Now, when we have when we conduct hypothesis tests on that, we can also construct a confidence interval. Okay, the confidence interval, finally, the confidence interval formula is this. Please pay attention. Pay attention. The confidence interval formula is this. You can see plus or minus, right? It means C prime X bar minus all of that. Then C prime X bar plus all of that. This is the confidence interval for multivariate repeated measure. For multivariate repeated measure, like I said, I want to investigate this guy, investigating the effect of hydration level, okay, on multiple physical tests over time. Okay, I wanted to take notes of that. Now, since I've given you formula, okay, we have an R code. How to do that now? R function for T squared with a contrast matrices. Do you see that? That's what you see. And I gave an example here. Okay, example of T squared with contrast matrices in R when it's not is true. I simulated data. When you want to simulate data, let's say you are not giving the real data, you want to simulate data, you need to set a seed. Okay, we set a seed so that we'll be able to simulate the same set of data. Okay, so if you write set dot seed and we put the same number, all of us, we're going to simulate the same set of numbers. Don't forget, we're simulating numbers randomly from distribution if you don't set a seed. Okay, if you don't set a seed, you're actually gonna the numbers, the figures the data you're gonna simulate will be different from mine. Now, you see, we simulated 10 data points. Okay, 10 data points for how many variables? Okay, for 4 variables. Take a look at that. And we can run a repeated measure. Look at that. RM.test. RM. R is repeated. M is measure. Okay, RM.text into your data set. I use excess to denote the data set. So what are you going to see? You're actually going to see the several p-values. Okay, so the first p-value here, the second p-value, okay, the third p-value. You can see all of that. You see the p-value, okay? So you'll be able to take a decision. Now, when you take a look at what I've done here, just for you to be able to see, okay, here is for 10 data point. This guy for 10 data points, and you can see the p-value to take a decision. For 100 data point, you see the p-value to take a decision. For 500 data point, because it depends on your size, your data size. I mean the number of observation. Okay, so take a look at that. So that generates p-value. And so I did one for when H naught is true and for when H naught is false. I repeated that for when H naught is false. Look at that. For when H naught is false. Okay, I repeated that for both 10 data point, for 100 data point, and for 500 data point. Take a look at that. Okay, now uh, that is all what I have about dependent sample. What I've walked you through today is I've walked you through how we can actually extend a PRT test, okay, a PRT test for two groups and a repeated measure ANOVA, okay, how we can, for univariate, how we can extend that to multivariate. I think I just walk you through that. Now, the next that I'm going now, I want to walk you through independent. How, how do we actually extend multivariate, okay, to, the one involving independence? And if I want to start, I'll first start with a univariate reminder. Okay, a sample t-test is very, very, popular in statistics and research world in general, where, I have two independent groups and I want to compare means. I have an hypothesis to compare that the difference of means is equal to a particular value and is or a difference of mean not equal to a particular value. Of course, if you take a look at this formula here, that is the test statistic for that. Okay, and SP here is a pool standard deviation. Of course, when you are conducting two sample t-tests, okay, we got situation where we make use of a pool variance formula, and we also have situation where we do not. Okay, now we have a pool variance formula here, XP. So this is just, and of course, this is to remind you of what you have done in the univariate case. Like I said, if you want to understand the multivariate case, you need to first start your journey from the univariate case. Because what we're going to extend is we are extending univariate into multivariate version of the test. This is the univariate case. Now, in the univariate case for independence, I just show you what we are testing for equality of the means. Equality of the means, okay, but we're focusing on one variable in two groups, two independent groups. We're focusing on just one variable. Okay, now I just show you the how to conduct the hypothesis testing for that and how to construct a confidence interval. Okay, so this formula now is a confidence interval for difference of means when you are using the idea of a pool variance. Okay, but how do we extend this test and the confidence interval to more than one variable? That's what we want to do now. To more than one variable. Now, to more than one variable, I'm going to start here, and that is going to be called multivariate independent sample t-square test. Okay? Multivariate independent sample t-square test. Okay, now we're going to, we believe, don't forget, how many groups are we working with? K represent the numbers of group. K, group 1, group 2. But in group 1, we're going to be focusing on more than one variable. In group 2, we're going to be focusing on more than one variable. Now, uh, if I want to use the idea of a pool variance, if I want to use the idea of a pool variance, I want to extend the idea of a pool variance in univariate case to multivariate case. Please pay attention. This is what I'm actually going to have. Please pay attention. Okay, now what is this? Oh, that is the sample covariance for group one. What is this? Sample covariance for group two. Does that make sense? Now, XP, the pooled sample covariance. You are pulling the two. Let me tell you this. We don't just pull them, okay? If I'm going to show you a text that we're going to conduct before we can assume the idea of pulling the covariances. Maybe we've tested the quality of the covariances. Okay, if the two groups have similar covariance structure. What do I mean by two groups having similar covariance structure? Don't forget, in the univariate case where you are focusing on one variable, assumption of one of the assumptions of a sample or of a two sample t-test is equality of the variances. Do you remember equality of the variances? If the variances are equal, I can pull the variance. Pulling the variance will actually increase precision and it's going to lead to a gain in statistical power. But situation where the two variances are not the same, if the two covariance structure are not the same, if you pull the covariances, that will distort the test, and that would lead to inaccurate type 1 error rate, and of course loss of statistical power. Now we're using the idea of a pool covariance, believing that the two groups have the same covariance structure. Two groups having the same covariance structures means similar relationship exists among dependent variables in group one and group two. That's what we mean. Now, after all of that, we're actually moving to construct what is going to be the test. This is the non-hypothesis of the test. Oh my God. Take a look at what I have right now. This is the Ottolin T-squared, the test statistic for the test. Now, in this Ottolin T-squared, you can see that SP. That XP is the pooled covariance matrix. Where do I get the XP from? Where do I get the XP from? Oh my God, there's a lot to do in midterm too. Okay, take a look at this. You see the XP here? How I got the XP, right? That's why I got the XP. Getting the XP is ensuring that you have the sample covariance for group one and sample covariance for group two. Then you are on the right path to obtain the pool covariance. Okay, and after all of that, you got a t-squared. Okay, and the moment you got a t-squared, then you should be looking for something to compare the t-square with. Oh my God. What are we comparing the t-square with? You're going to compare with this guy. We're going to compare with this guy to be able to know whether to reject H naught or not. Okay. Now, now that is that. Then the simultaneous confidence interval can also be derived. Of course, the probability of a t-square less or equal to that would be equal to the level of confidence I call 1 minus alpha. But I'm going to show you. So I have a coding now for that multivariate independent sample test function. Okay. So take a look at this. I'm assuming data set, and you can see what I have. This is conducting multivariate, the t-test now for independence. Okay, so take a look at that. Okay, and here when you are the t-square that I'm using now, I'm assuming no asymptotic. Do you see that? I'm assuming no asymptotic. That is why when you see a type, asymptotic false, asymptotic false, asymptotic false, which means this can be applied to small sample size. Okay, I'm not talking about a large sample size here. Okay, please pay attention to the code. Okay, Now, I think I've shown you how to conduct the test, the multivariate version of independent two-sample t-test. Now, uh, we have for a finite sample, we have for a large sample p-values, and what is going to be the difference. The only thing is the same code, except that when you come to type, take a look at it. Asymptotic false, asymptotic true. Do you see that? Asymptotic false is when you have a finite sample. Asymptotic true is when you have a large sample. Does that make sense? So that will give you a code, a way to compare the two, whether you're working with a finite sample or you're working with asymptotic. Whenever you hear asymptotic, we're talking about large. Okay, so and this is simultaneous confidence interval for that. You see the simultaneous confidence interval, XP, don't forget the XP is the pool standard deviation that we got from simple variance. Okay, take a look at that. Now, uh, you can see that, and this is the code in R. I will advise that you revisit the code in R. Okay, we got a lot here. That's the code in R. And lastly, before I go, I told you the other time, how do we investigate whether the two groups have the same covariance matrix? Because it is only when they have the same covariance matrix that you can pull them together. That you can use the idea of a pool or covariance structure. And how do we test? This is a test for the homogeneous covariances. We have a test for that. Now let me tell you this. If this test fail, we cannot use the idea of a pool covariance structure, but what other ideas can we use? We can use number one, there's a generalized t squared. Okay, when this assumption fail, okay, the alternative as our test that can be that we can actually use, okay, number one is generalized generalized t squared test. Number two is permutation test. Okay, permutation test. Number three is maneuver, maneuver with weak lambda. We're still going to talk about this is an alternative test when the two covariances are not the same. When the two covariances are not the same, this is going to be the test that we can conduct. But when the two covariances are the same, then we go with the pool variance one. Now, if I want to test, for the two covariances, what am I going to use in the testing? Okay. Now, I think what I'm going to do, I'm going to start from here on Friday, because on Friday, yeah, I'm gonna start. So what I'm gonna start on Friday is how do we test for equality of the covariance? How do we show that the covariance of this group is the same as the covariance structure of the other group? Because it is only when the covariance, okay, structure of the two groups are the same that you can actually use this, okay, that you can actually construct a confidence interval test hypothesis, you know, using what I have here. Okay, you can see the XP is a pool. Okay, the idea of pulling the sample covariances, we got that idea from the equality of the covariances, and there's a way we can test. So what I'm going to start on Friday, I'm going to start from how do we test the covariance structure of the two groups are the same or not. When the covariance structure of the two groups are the same, we're going to make use of this particular formula that I'm showing you here to test hypothesis, and of course to also construct a confidence interval, okay, to conduct statistical inference in general. You can see the confidence interval formula, the test statistic formula involve a pooled covariance structure. We're only going to do that when there's equality of covariances. But if the equality of the covariances is violated, we cannot use that. And so what is the alternative that we can use? One of these. It could be a generalized t-square test that is adjusted, okay, by Sutter weight correction, okay, the permutation test or maneuver with lambda. This way I'm going to stop today. Is there any question before I go? Like I said, this is becoming complicated. If I were you, because I want everyone in this class to have A, if I were you, if you find yourself struggling, please reach out. Make sure you all stay safe. The weather is extreme. I will advise that you're careful when you're driving. Okay? Stay safe. See you on Friday. Bye for now, everyone.